Okay, welcome to the lab seminar, and today we have a postdoc candidate, Dr. Mamuti, giving a talk, and Dr. Mamuti received her master's and Ph.D. degree in optical engineering from laser laboratory, Chiba University in Japan, and her graduate research mainly focused on the generation of tunable infrared structure laser, and after graduating, she worked as a postdoc research at the laser lab, and she has received a number of research funding from Kobayashi Foundation, and she has been working in the laser science lab at Tokyo Technical Institute to develop optic trapping and macro nanoparticles. And today she's going to talk about tunable infrared structured laser generation and opto-thermal trapping of micro nanoparticles. That's what I'm doing.
Thank you for the introduction. Today I'm going to talk about the tunable infrared structured laser generation and opto-thermal trapping of micro nanoparticles. First of all, I'd like to introduce myself. My name is Roukuya, and my hometown is originally Artu City in northwest part of China. And I graduated the University of Tunable University, and my major was physics. And after graduation, I worked as a technician in a medical chemistry lab in Chinese Academy in branch. And after that, I got this job in my hometown in a middle school that I teach the physics subject. And after 2 years, I decided to pursue my education. I quit my job and go to Japan, and then I enrolled in Chiba University for the master's program, and I continued the PhD program at the same university. And after graduating the PhD program, I worked half year in the same laboratory that I graduated, and after that, I got the postdoctoral position in the laser science laboratory in Toyota Technological University. In that laboratory, we worked on the optical trapping. The outline of my talk is as follows. First of all, I would like to introduce background of our research, including optical vortex and optical parametric oscillator, and also optical trapping. And today I want to talk about 3 projects, including generation of multiple orbital angular momentum from the optical parametric oscillator, and the second one is generation of orbital angular momentum, and the last one is opto-thermal trapping of micro and nanoparticles. In 1992, Professor Ali's group newly defined the orbital angular momentum of light. In this paper, he addressed that the vector difference between the direction. Let me get the pointer. Okay. He addressed that the vector difference between the direction of light propagation and the direction of the pointing vector induces the orbital motion of the particle in the beam cross-section area called orbital angular momentum. Since then, the orbital angular momentum of light has been explored further from the fundamental theories and quantum nature of light and the light-matter interactions. The optical vortex is a general term for light having spiral wavefronts, exhibits orbital angular momentum owing to its phase singularity and its centrality beam profile. The most conventional example for such a light beam is the Laguerre-Gaussian mode. For Laguerre-Gaussian beam, the IG mode is written as follows. In this formula, light beams exhibit azimuthal phase structure exponential IL pi, where L is called topological charge and commonly taking an integer value based on its boundary condition, and exhibits orbital angular momentum of L8 bar per photon. Because of its unique properties, optical vortex has been attracted great interest and utilized for various applications. The most interesting application of optical vortex is that it can create micro and nano structures, also control the periodic acoustic metal and polymer spiral structures. These results came from the same laboratory as Roukuya. They use the optical vortex to create such chiral nanostructures and use this to use some advanced technologies. Another new finding about optical vortex is that the super-resolution microscopy, in which vortex light used for a depletion with the fluorescent light so that microscopy exceeds the diffraction limit.
There we go. Yes.
Next, I want to talk about how to generate optical vortex in conventional way. There are many convenient ways to generate optical vortex. One of the common methods to generate optical vortex is by a spiral phase wave, composed of a surface of helical and spiral phase steps. It adds a helical element to the wave, plane wave. However, the spiral phase plate is designed for specific wavelengths. We have to use different spiral phase plate to different wavelengths of laser. Another method is spatial light modulator, mainly composed of holographic diffraction slit, which will modulate the amplitude and phase of the input. However, this method suffers from the diffraction loss and low damage threshold. Here. Okay. To match the absorption band of various materials, it's necessary to generate tunable optical vortex in the near infrared region. So in this research, my goal is to generate tunable lasers. So next, I would like to introduce the nonlinear frequency conversion process. In the nonlinear frequency conversion, the optical phenomenon is this kind of optical phenomenon in which when a very strong electric field is incident on the nonlinear optical crystal, second order and third order nonlinear polarization is generated and the wavelengths of the light is converted. So the second harmonic generation and sub-frequency generation is two types of conversion process, and for the down conversion process, the optical parametric oscillator and different frequency generation. Using this up conversion process, we can tune the wavelengths of signal and idler really freely. Therefore, these methods are really efficient tools to generate tunable vortex lasers. So in order to generate a widely tunable optical vortex, the following optical parametric oscillator is designed. As we mentioned above, in this process, the one photon splits into the two photons, so the wavelengths of the two generated photon is widely tunable. Generally, the oscillator consists of a resonator and a nonlinear crystal inside. And in this process, the energy and momentum are conserved. And we also try to investigate conservation of the topological charge. The first thing we must consider is to construct a singular resonant cavity, because the resonant oscillator resonates signal and either at the same time. So as a result, topological charge of point light is shared between signal and either. Therefore, by designing a resonator that resonates one of the output, the topological charge is selectively goes to either one of them, signal or either. Secondly, to prevent the walk-off effect of the crystal, a nonlinear phase matching crystal is necessary. In this critical phase matching, a slightly angle shift causes a large phase mismatch. On the other hand, in the non-critical phase matching crystal, the refractive index depends on the temperature of the crystal, so the phase matching is achieved by changing the temperature. Therefore, we use the alveolar crystal as our nonlinear crystal, as it has some advantages like high damage threshold and wide acceptance angle and less walk-off effect. So this is experimental setup. Our method to control the topological charge is as follows. To generate 3 states from the cavity, we only use one crystal to make the cavity as short as possible. The parametric cavity is a singly resonant cavity for the high energy photon, the signal. In this case, the parametric gain can be written by the spatial overlap of the electric field between the front beam and the signal output, where Ls is the topological charge of the signal. So from the overlap efficiency factor, we can estimate which order vortex mode is dominant in the parametric cavity. This graph shows the spatial overlap intervals based on the signal output with the topological charge of 2 and 1 and 0. In the extended cavity, the spatial overlap efficiency is calculated to be below 1. Therefore, the signal output lays at the fundamental Gaussian mode. Instead, either output will be expected to be first order vortex. In the extended cavity, the efficiency of first order is higher than the second order mode efficiency, so that cavity encourages the signal output lays at the first order mode and cause the generation of Gaussian mode either. In the further compact cavity, the parametric gain of the second order mode will be more dominant, so that the signal output will be expected to second order, and either output might be minus first order vortex according to its orbital angular.
So the input has a angular momentum while the output have to have a conservation. But how do you control which one output is from signal? What, like how do you control which angular momentum output at which channel?
We control it by extending the cavity length. In this case, like in this length, it goes to the signal and either with Gaussian.
Oh, okay. So those are depends on the cavity.
Cavity length.
Are they quantized or you continue changing the cavity?
We just did all of the extent to all of the cavity lengths, and then we try to find out the conservation of the topological charge, that the topological charge goes to signal or either, and it changes really suddenly, so at one point.
Okay. So is there any advantage compared to just typical oscillate with TE00 mode, just typical Gaussian beam input?
Yes.
In terms of efficiency?
Yes, exactly. From the Gaussian beam, you cannot observe the vortex out beam, probably. But for example, the input is vortex beam, so the output we can generate a vortex beam for either for the signal or either. The schematic diagram of the experimental setup is as follows. The pump laser used was a conventional frequency double Q-switch neodymium laser with a wavelength of 532 nanometers. The pump laser out with a nearly Gaussian spatial form was converted into first order optical vortex by the spiral wave plate. This is the spatial form of the input. The loosely focused optical vortex was injected onto the optical parametric oscillator. The nonlinear crystal dismantled on the top of an oven, and then tune the wavelengths of the signal and the audio output. By using the one-dimensional translator, we performed the experiment in various cavity lengths. The signal and audio outputs were separated by a divergent mirror here, and then were observed by a CCD camera. We also investigated the wavefront of the signal and audio outputs by sharing interferometric technique. The positive and negative first-order beam are collected by a lens to the camera, so we can get a fringes of the beam, so we can measure its topological charge. Here, two downside and upside for means that its topological charge is equal to 1. So this is actual look of our opto-thermal oscillator, and this is the crystal, and its temperature is tuned between 110 to 157 Celsius. And this is experimental setup. These are the spatial form and self-interference fringes of the signal and audio outputs. In the extended cavity, the signal shows a fundamental Gaussian, and either shows the first-order vortex mode. And here we can note that the topological charge of pumping transfer to the signal output. In the compact cavity, the contrary to its former one, signal output exhibits annular profile, which is first-order vortex mode, and either out shows a Gaussian mode, and then its strength also shows no form. The further compact cavity is the most interesting one. The further compact cavity for the signal beam enables lasing both of the signal and either in the vortex mode with the annual intensity profile. The signal self-interference shows a pair of three-legged upward and downward forks, and the either also shows the annular form. And then we checked its topological chart, and it's -1. So in this case, like in the short cavity length, the topological charge of the signal is 2, and for the either it's -1. And then this graph shows the tunability of 3 state modes, and generally the signal and either outputs are tunable in the wavelength range from 816 to 950 nanometer for signal, and for the idler correspondingly it's 1207 to 1760 nanometer. In the case of compact cavity, a maximum signal vortex output energy is 2 millijoule, and it's for either it's 1.5 millijoule. Another method we realized to control the orbital angular momentum of F is by tuning the wavelengths of the signal in the compact cavity. As we demonstrated before, the compact cavity, the system provides a second-order signal and negative first-order either output. When the wavelength region is shorter, this system allows the signal output to laze in the unexpected third-order vortex beam, and for the either, it's negative second-order vortex beam. This phenomenon can be understood by employing the spatial overlap efficiency between the pump signal at various signal wavelengths. In the shorter wavelength region, the overlap efficiency of third-order vortex is higher than the second one here. And in the larger wavelength region, first-order efficiency is dominant here. So from that calculation, we also did the experiment that in the shorter wavelength region, we can get a third-order signal, and correspondingly the minus second-order either. And for the middle region, as we mentioned in the earlier slide, second order and first order either. And the larger wavelength region, we can get a first order signal and a Gaussian beam for either. And its tuning range is from 745 nanometer to 970 nanometer for signal, and the corresponding either is 1178 to 1860 nanometer for either with different topological charges. So to conclude the first project, we generated the versatile optical vortices with different versatile topological charge, including upconverted and negative orbital angular momentum from a nanosecond vortex pumped LDO and optical parametric oscillator by appropriately shortening or extending the cavity length. The system is compact cavity configuration is also generation of the allows the generation of the signal out with a 3, 2, 1, 0 and minus 1, 2 of topological charge by simply tuning the temperature of the crystal. So to generate higher order versatile optical vortex, we conducted the experiment with the second order pumping beam. And the topological charge of the output results assigned by the tilt lens technique because the output's topological charge is higher. So in this technique, the vortex beam passes through a cylindrical lens and splits into topological charge plus 1 of logs. So from the number of the logs, we can know the topological charge of the output. So here are the experimental results. When we pumped the optical parametric oscillator with the second order pump beam in the shorter wavelength region, here we can get a first order vortex for signal and negative second order for either. And in middle region, third order signal and negative first order either. And in the larger wavelength region here in the green area, like we can get second order signal and the Gaussian beam. So this is another interesting topic that after the optical parametric oscillator generating the vortex beam. As mentioned above, the typical pure optical vortex shows a ring-shaped mode. On the other hand, the flower mode shows a several petals as shown in this figure. A flower mode generated from an optical parametric oscillator has many advantages, like equally distributed petals and wavelength tunability and the visual level of energy. And it is really easy to control the orbital angular momentum of the outputs. So in next topic, I will focus on generating the flower-shaped vortex beam. So these are the applications of the flower beam. Recently, the flower vortex mode is like rising interest because of its potential applications. The typical example of flower mode's application is particle trapping. This experiment includes 3 steps. In the first step, optical vortices with opposite topological charges are prepared to generate a flower mode. And then by evaluating the flower mode, they generated micropillars like this. In the last step, these micropillars used for microparticle trapping. Apart from this, flower and wheel-shaped modes have applications including optical manipulation, quantum encoding, and free space communications. So our goal is to generate tunable near-infrared optical vortex with flower-shaped modes. The experimental setup is identical with the previous one. However, the pump source is a shorter coherent time, like 15 picoseconds, which is much shorter than the intra-cavity range time of the photon. This would allow the cavity to operate under the condition of near optical parametric generation, thereby enabling the creation of the entangled orbital angular momentum states. In the parametric cavity, both positive and negative vortices exhibit the same spatial overlap of intensity profile in the pump. Thereby, the efficiency generated in both vortex modes. This is why the opposite signs of the vortex modes coherently overlap each other and produce flower-shaped modes. Next, I would like to introduce the generation of coupled orbital angular momentum. The overlapping of two propagating LG modes with opposite value of topological charges, the beam interference constructively at angles where their phases match and destructively in between. So they can shape a flower-shaped modes. So in this case, its topological charge is 4. Alternatively, a pair of Laguerre Gaussian beams with the opposite topological charges but different value of orbital angular momentum generate the dark intensity regions surrounded by bright light called the wheel-shaped vortex mode. Complete constructive and destructive overlapping interference requires equal light intensity and coherence. Therefore, the superposition occurs at the radius when the light intensities of the two beams balance. These are the experimental results. Flower-shaped signal and idler are generated from the parametric oscillator. In the shorter wavelength area, we can get a force order and negative force order at the same time. So they couple it together and then give us like 8 petals of beam shape. And in the idler, its topological charge is outside the ring is 6 and inside is -2. So it shapes a wheel-shaped mode. And in the between wavelength area, we can get 3 and -3 for signal and for the idler, -1 and 5. And in the larger wavelength region, we can get the second and -second, negative second flower-shaped mode. And for the idler, we got a Gaussian beam inside, and the outside ring is the force order optical vortex.
So those are post-laser, right? These are not continuous laser.
This is CW laser.
CW.
So the energy for the signal is 1.1 millijoule, 1.2 almost, and for the idler is 1.5 millijoule. And the optical efficiency for signal is 15, and for idler it's 6.3%. And this is the theoretical calculation of the signal. Such flower signal mode should manifest the entangled orbital angular momentum states. That is the coherent superposition of two orbital angular momentum with the opposite topological charge, given by the following formula. In the whole tunable wavelength range, the system allows the signal out to laze in the second and third and fourth order entangled orbital angular momentum states, thereby yielding the flower mode with 4 and 6 and 8 petals. This theoretical formula supports the experiment very well. And for the idler, the simulation is as follows. Like in the zero on like Gaussian beam and the force order vortex coupled together, and they can make a wheel-shaped like this, and the experiment is also shows generally the looks like it, and the experimental results and the simulation of the negative smaller order and positive larger order orbital angular momentum results these wheel-shaped vortex move, and from this whole optical parametric oscillator process, the orbital angular momentum is conserved. So in conclusion, we have successfully generated widely tunable optical vortex states from a non-critical phase matching LBO optical parametric oscillator with a simple linear cavity configuration. And we have demonstrated the selective control of the orbital angular momentum of the signal and either output by tuning the spatial overlap of the pump and the signal output. Most interestingly, for the first time, we generated multiple entangled orbital angular momentum states, including upconverted and negative states. And by equivalent coupling, we achieved superposition of outputs that can produce flower and bead-shaped modes. And my third topic is about opto-thermal trapping of micro and nanoparticles. This is the research I did as my postdoctoral project in the Laser Science Laboratory in Toyota Technological Institute. This is the introduction of opto-thermal trapping. When the laser is introduced to the water is heated up around the focus to use laser absorption. Then the particle is driven from cold to hot regions along the temperature gradient when the sign of the Sorel coefficient is inherited. Typically, to gain the temperature gain, the laser energy needs to be converted to heat through certain light-absorbing materials, which is transferred to the surrounding energy to the water solution. In opto-thermal trapping, the thermal diffusion allows the micro-scale manipulation of the small particles and molecules as they drift along the temperature gradient. For example, the temperature pattern DNA was written into water film in an overall cool chamber at 3 Celsius. On the other hand, when its temperature is in the room temperature, the DNA is thermophobic as seen by the dark letters here. Moreover, the size-dependent separation of the DNA on the plasmonic substrate by means of plasmonic optical thermal trapping is realized. Then they use the plasmonic optical tweezer to trap DNA of 2 different lengths dissolved in solution. The DNA were creating a double micro ring pattern with the shorter size DNA and the larger one forming a smaller and larger rings respectively. Here. So in these recent years, a metallic film coated on the substrate is one of the common platforms using plasma-enhanced opto-thermal effect. The temperature gradient is achieved by the strong coupling between the light and matter-based surface plasma resonance. In this case, substrate is prepared by coating a gold film into the glass slide. These experiments using the intermediate materials, which is indirect to transfer the laser energy to the solvent. In our experiment, we use a 2-micron laser, which is 6 times more efficient than the conventional trapping, as it has an absorption peak here. The laser beam can be directly and strongly absorbed in the water solvent without intermediate materials. And we can use a very small power, which does not damage the object. And this method can trap the particles from a relatively large region. So we use 2-micron continuous wave tuned fiber laser as a pump laser. The output laser from the fiber is columnated and reflected by a divergent mirror and focused at the bottom glass solution interface. The exact wavelength is 1956 nanometer, and the columnated beam is as shown in here in this figure. And then we use after the reflective type objective lens, the profile matches the simulation very well here. And we can achieve the focusing spot as shown in this figure. First, we conducted the experiment of 1 micron polystyrene particle in water and heavy water solutions. Sodium chloride is slightly added to the solvent in order to weaken the surface charge around the particles to form a relatively stable assembled structure. When the laser is turned on, the particles are gathered one by one toward the focal spot in the water. When the laser irradiates the sample in the heavy water, no particles are trapped at the focus.
May I ask a question?
Yeah, sure.
Is the particle moving or the fluid moving? I mean, fluid move the particle there, or the particle, what's the force?
I think the solution itself also moving because it gets the energy from the laser energy, some heating, and the solution heat, and then gather the particle together.
What's the size of the particle?
For this one, it's 1 micrometer.
May I add here? So, if the temperature cools down later, will the particles move again? So, is this process reversible?
Sorry.
So if you apply laser, the temperature will go increasing, right? And particles moving.
Yes.
And then if we give some time, the temperature cools down.
Yes.
Then the particles
Yeah.
move again.
Yeah. If you turn off the laser, it will disperse as shown in this figure. If that's what you're asking. If the solution loses the heat, it will disperse all of the particles. Okay, this slide shows the temporal evolution of the assembly. Before turning on the laser, the polystyrene particles are homogeneously dispersed in the solution. When the laser is turned on, the particles are gathered one by one for the focal spot. In 20 seconds, the particles are trapped at the laser focus, forming a monolayer of hexagonal closed packed structure, and its assembly size gradually grow over time. When the laser is turned off, the assembly disperses all of the particles without any damage on the particle itself. We also conducted a longer irradiation time exposure experiment. As shown in this graph, in 2 minutes of irradiation, the assembly size almost approached steady state. In 10 minutes of irradiation, the assembly is formed a multi-layer circular shape with a diameter of 42.5 micrometer. When the laser irradiates a sample in heavy water here, no particles are trapped at the focus. To find out the origin of the different manners between water and heavy water, we measured the laser power before and after water and heavy water sample changes to estimate how much the laser is absorbed from the cell to the solvent. This simple estimation shows that the laser is absorbed to the water more than 2 times than the heavy water. This indicates that the temperature elevation is indeed the origin of aggregation of the particle at the focus. And this slide shows the power dependence of the trapping. With the increase of laser power, the particles are trapped more intensively. When the power increases to 45 milliwatt, all the particles are rapidly collected first and then cause a damage on the sample because of the absorption of the polystyrene particle itself. Here, each transmission image is recorded after 20-second laser evaluation under different laser power. The trapping threshold is approximately 1.5 milliwatt, which is the laser power we can be able to distribute several particles around the focus. The maximum power will be around 30 to 40 milliwatt, and the number of the trapped particle is linearly increased as the irradiation power increases. We also tried the trapping with the different size of polystyrene particles. As the smallest particle we examined, the concentration of 200 nanometer polystyrene nanoparticles increased as focus after tuning on the laser, and closed hexagonal structure are formed for the 500 and 1 micron and 2 micron particles. We carried out the experiment with a single particle trapping by reducing the particle concentration. We put the particle to the right side to the top here, and then try to collect the particle. And the XY coordinates of the particle in the focal plane are extracted by image analysis. This graph shows the trajectories of each particle, 500 and 1 micron, 2 micron particles. First, it can be observed that the trajectory of 500 nanometer polystyrene particle is fluctuating more than the 1 micrometer and 2 micrometer ones, because of the motion of smaller particle is much more dynamic due to Brownian motion. In addition, the maximum velocity of 500 and 1 micrometer particle is both around 8 micrometer per second, and that of 2 micrometer particle is slower, around 5 micrometer per second. Regarding to the particle confinement at the focus, the larger particle tend to be much more confined than the smaller ones. Here. Which may due to the less fluctuation of Brownian particles. In detail, 1 micron and 2 micron polystyrene particle are confined in a circle with a diameter of approximately 2 micrometer. The width of the trapping potential well becomes narrower for the large particles, and correspondingly, the trapping stiffness for the 500 and 1 micrometer and 2 micrometer polystyrene particle is about 7 and 0.04 and 0.08 respectively. To show the present method can be used for other materials, we demonstrate experiment with PMMA and silica particles, which are also typically used as the standard targets for trapping. And for all of the cases, the particle size is 500 nanometer. And from this transmission image, we can know that in all of the cases, they can trap the 500 nanometer particles to the focusing spot. So next, for extending to the 2 micron trapping, we also wanted to do the experiment with 3 micron laser. Here I show the advantages of 3 micron mid-infrared laser. As the water absorption peak is around 3 micron region, trapping with 3 micron will be much more efficient than the 2 micron laser trapping, and we can use very small power of laser for trapping. So this is the experimental setup for the 3 micron trapping. We built this 3 micron laser system. It's a home built fiber laser based laser system. But the out laser will be generated from erbium sibilant fiber here. By using a grating here, we can tune the wavelengths of the output, and then the trapping system is the same with the 2-micron trapping system. And the wavelength dependency of the optical trapping on the different material will be investigated, as we can tune the wavelengths of the laser system by tuning the angle of this grating. And the typical wavelengths are shown in this graph. And this gray area is the absorption peak of the water. And we can know that in different wavelengths, it shows a different absorption. So we can do research about like wavelength dependency on the opto-thermal trapping. So these are the different wavelengths profile. So this tuning range is 2.7 micrometer to 2.8, almost 2.8 micrometer, and the central wavelength is 2.76 micrometer. So I compared the trapping of 2-micron and 3-micron microparticle trapping. Here are the 1-micrometer polystyrene particle trapped by the 2-micron laser. That it can reach to the maximum point to the 45 milliwatt, but in the 3-micron, it can cause a damage in 10 milliwatt power, under 10 milliwatt power, and its threshold is also really low. So we can use the 3-micron trapping that to the some applications that that requires really low threshold and really low power. And then we plan to build a biolab to do the research about using the method to living cell. The research is still on the progress, and the 3-micron and the living cell trapping is now they are doing this research. So I'm going to publish the 3-micron trapping in like in these two or. I'm gonna skip the results. So in conclusion, we have successfully demonstrated the opto-thermal trapping and assembling of micro and nanoparticles within 2-micron cilium-doped fiber laser. The wavelength used in this present study is the longest wavelength, which is directly and strongly absorbed in the water solvent. The present system can be extended to various fields such as biosensing and DNA detection and sorting without fabricating light absorbers and substrates. Thank you so much.
Time for question.
So what's the beam size for this, for the cutting span? I mean, for this result, what's the beam size?
Beam size?
Yeah.
Beam size is, let me show you that figure. Here. The beam size is around 30 to 40 micrometers. So the focusing size is like this small.
So with a very small focusing, you can type in around, and for that result, it seems like millimeter typing area.
Yeah.
So it's affected. It's mainly affected by the beam size or the thermal effect. I mean, if I increase the beam size, is the tracking area becomes larger with the same optical fluence.
I would say the intensity of the laser is important in this situation. Like, if the intensity of the laser is stronger and it can give the water solutions more energy, it can trap a lot of particles. But if we lower the focusing size, like if we make it bigger, it cannot trap really efficiently. So we also did that experiment too. and it didn't go very well. But still, it can like pull some particles because the energy of the laser goes to the water. So it can pull some particles, but cannot trap really efficiently. So here the size and the intensity is important in this condition.
Yeah, that's true. Yeah. Okay.
It's different shape of the vortex beam, have different performance in particle control, and how you choose the beam shape mode.
This flower shaped models.
Yeah, I mean, we want to do the particle control. That's like vortex equals to topological charge 1 or 2 or flower shape have different performance, and you compare the performance of them, and how do you choose the one you want?
Can I ask you a question again? Sorry.
So, I mean, we'll do the experiment. We want to control the particles, right? Are you using the flower shape or just a topological charge 1 or 2 or larger? And are they different in the performance of the particle control?
Oh, okay, I see. Thank you for repeating your question. I see your point now. So the flower shaped beam, we use the topological charge of 2 as a pump, and then as an output, we can get the higher energy photon for signal and lower energy photon for idler. And then for the signal, we can get in different wavelengths region, we can get these kind of flower shaped modes. And for the idler, we can get this kind of wheel shaped modes. And you also mentioned that the trapping.
Yep.
Yeah, we didn't use this flower shaped modes to the trapping directly yet. But I showed you the application of trapping. Maybe that's what you're asking here. That in this paper, in the first step, they generated the vortex beam of opposite topological charge, and they overlapped each other, and then it shows their flower-shaped mode. And then using this flower-shaped mode intensity, they can irradiate this laser to the material, and then they can get this kind of pillar. And using this pillar, they trap the particles.
Yeah, I mean,
It's not like a direct
generate different shape of the flowers, right?
Sorry.
You can generate different flower shape of the vortex beam, right?
Yeah.
But I mean, in the trapping performance, is the beam of the shape will affect your energy and trapping efficiency.
Trapping efficiency. Oh, I didn't try to trapping by flower-shaped ones. These are different type of projects. Like I generated flower-shaped modes at first, like that's my second project, and then I moved to the opto-thermal trapping by just using flow-shaping.
So in the video, very nice video, I saw some semi-transparent things move to the beam too. Are those bubbles?
Oh, okay. I see. In the trapping video.
Yeah. Right, are those bubbles?
These are not bubbles. It's just the particles in different depths.
Oh, but it seems like there's some kind of clapping explosion. It looks like an explosion.
But it goes to the central focusing spot and just goes into different depths.
I see.
Like flows into the
Just a
different
visual
depths.
illusion looks like an explosion.
Yeah.
Another.
The chamber thickness is 120 micrometer thick, so it has like different depths. So this is the bottom of the sample. So we trap the particle at the bottom. But in the different depths, we cannot see clearly the particle. It looks like this, and it just flow away. Yes.
If there are bubbles, will the bubbles move or collapse, things like that?
I never see bubble in this tracking.
Okay.
So.
Just last question. Your animation looks very interesting. Which software do you use?
For that, I always use the Python to visualize that kind of things, and then in this calculation we use Python first, and then for the visualization we use the 3D Max to visualize the coupling of the two things.
I just ask another question. For the tracking experiment, so your advantage is you don't need the substrate. Right?
Yes.
So if without the substrate, can we see the 3D distribution of the particles? So do you see maybe the vertical distribution?
Yeah.
And do you see that one?
Oh, okay, I see.
And different focus depths.
Oh, okay. Oh, okay, I see. Yeah, we in this experiment we just focus the laser to the bottom part of the sample, like the bottom part, and then we collect the particles of this bottom part of the sample. So we didn't do we didn't change the height to collect other particles, but we only did this experiment on the bottom part. So we didn't really focus on the higher depths of the solution.
So does the distribution of the particles similar like the thermal distribution?
Yes.
They are similar. So the center part is density, and maybe the surround part is sparse.
Yes.
Okay, so if I consider the 3D distribution, so they should also similar like the distribution.
Yeah, for this 3D distribution, it would like if it's focused on the bottom, and then it just disperses on the higher part, so it can its focusing point is on the bottom, so it only collects the particles on the bottom, not like it can like it goes to the like this on the higher part. So in the higher part we couldn't observe any particle trapping, just some flowing, like.
I think the question is the force large enough to fight the gravity?
Oh, okay.
Do you think the force from the general thermal trapping the force large enough to fighting gravity?
Yeah, I think so. Yes. And we also try to make some changes to this setup to irradiate the sample from the top. And in that point, exactly we can find out the gravity and then the other things contribution to the optical trapping.
Another question?
I have a quick one.
Okay.
Between the two lasers, thulium and erbium, the absorption coefficient is much higher on the erbium, but the trapping was pretty similar. So even though the absorption coefficient is probably 6 times higher, you're getting like 3 times, maybe 2 times on the trapping threshold. Could you comment on that? If it's only heat, because it should heat up faster with the erbium.
With the erbium, we didn't use any thermal. We didn't use the thermal cooling, like cooling system for the silicon fiber, but all the setup is
No, I meant on the trapping, not on the next slide. If you where you compare the two trapping between, yeah, it's the slide.
Yeah.
On the 2700 nanometer,
Yeah.
the absorption coefficient is like 10 times or 8 times higher.
Yes.
But the trapping efficiency is only half as good.
Yeah.
If it's only heat, could you comment on if heat is the mechanism, it can be much more efficient with the 2700 because the spot size is the same.
So yeah, we also estimated that the 3-micron particle trapping would be like much more higher efficiency than the 2-micron trapping. And then in the result, we couldn't see this dramatic efficiency as you said. But still, we conducted this experiment with the different wavelengths, with these 5 wavelengths. Like in the absorption in 5 wavelengths are different. So we can compare between like how many and how efficient the wavelengths contribute to the trapping. So in the result that we can see the difference between, like we can see clear difference between these wavelengths independence. So in this case, like the smaller wavelengths and higher wavelengths, they can up to 1 or 2 times more efficient than this one. And then still, that's not what we expected. We expected much more efficiency from 3-micron. So we are still working on it. But it's really important question.
I guess it's not only depends on the absorption code, but also depends on thermal diffusion, temperature specification, and then the viscosity effect. When it's too fast, they will be limited by how fast they can travel. That's my guess. I don't know anything about travel. Maybe let me ask a question first. So in one of your beautiful pedal, multiple thermal. Can you go that picture? So you talk about lithography. On the go one of the application in lithography. Yeah. So if I look at the dimension, they are close to a micron. Right? So if it's a 1 micron structure, I can just generate a pattern without that fancy octangular momentum. So what's the advantage to using those high L mode to generate those patterns?
Yeah, this flower mode is like they are evenly distributed. So if you can observe that they are at the same height, and then you can get the really quality pillars from the flower mode. And then
so what's the wavelength for this case?
For this case, I think it's 532. I'm not sure. I forgot about this, but it's not infrared.
So for 500 micron, I can generate with my filter and mask. I can generate those kind of structure without using angular momentum beam. I'm just wondering, is there any advantage for that?
So, like if we mention about the advantages of the vortex, like it would be like it has the orbital angular momentum that the Gaussian doesn't have. So I think.
But for lithography, you don't need only the explosion of that parts. Or maybe their depth of focus is better.
I will think about this problem.
Okay. Is there any other? Can you speculate what other application for those flower petal, and they're beautiful pattern.
And then we also like, I wanted to try to use this flower pattern to the trapping. Like for if you irradiate flower mold to the sample, you can collect like the flower shaped particles. And then this vortex beam has the orbital angular momentum, so it can rotate the particles. So what we were thinking is that if we put some cell or put some particle inside this trap of particles and can move it like a motor, like we can generate a micromotor.
I missed a lot of your talk, so I apologize for that. I got stuck in another meeting. So I just to ask first a statement, then a question. The statement is obviously your OAM beams are part of a complete basis set. So by superposition of OAM beams, you can generate any image that you want. Do you find, sort of in answer to Zhongping's question, that when you use something like that, the darks are darker than they might be if you use lithography, and the brights are brighter? And then second follow-up question on that is that with the beam having an azimuthal pointing vector, do you see that the protrusions that you get actually follow the direction of the light, or simply based on the intensity of the light?
It's just intensity.
Just the intensity. Yeah. So you don't see them like spin round or anything like that.
No,
Great
we
spirals.
just check the profile.
Okay. Thank you.
Another question? Quick question.
I want to back to our first topic. The question is that possible to generate a higher mode of the vortex beam, like a topological charge rather than flow, or much higher? And is there a limitation for that?
Yeah, for my experiment, we generated the first order vortex beam from a second order beam. So the highest topological charge I get from second order vortex beam is 4 for sigma, and that would be -2 for either. And for this coupling, like +4 and -4 for signal, and for either it's up to like 6 and then -1. Like you can get the 6th order for either and the second order of the vortex like inside. So that is the highest order I get from my experiment. But maybe if we conduct the experiment like pumping the ovule with higher proportional charge of the vortex, for example 3 or 4, maybe we can get a more bigger vortex.
I think the short answer, if you can think of what application, someone will generate it for you. On that note, let's send to the speaker again. So, Chris is at 130, maybe 135.